Now it's like, so we were just now started the quadratic form. So first of all, what is the quadratic? So quadratic is generally denoted as the degree of, kind of uh, generally called as a polynomial. So called for polynomial. So if it is of this case, okay, or maybe each time we can keep x square base vx square, but here it is, let's keep as the same here, this one. So this is a polynomial of degree 2. So quadratic is named from the degree of a polynomial. So quadratic form is generally, we have, suppose this is a one variable, but if you think about this case ax square, okay, think in the two variable case, even in two variable only I'm saying. So this is let's say 2bxy, or even just a bxy plus cy square. So here you can see there is no constant. We are considering only a kind of this form. You can check here the degree of each term. Here the degree. So quadratic is here. The degree of this term is 1. Okay. But this is just a quadratic polynomial we call. But we are not going to consider it here. So quadratic form is a form of this. Generally we call this one. If you can see here the each term have the degree and there is no constant. So this is a quadratic form, and two variables. Okay, so in more general form we can think. So this is actually relate a matrix. We can this relate to a matrix where we can think like this: x and y, and then matrix, and then vector x and y, where the entry is going to be here a, b by 2, b by 2, c. So if you multiply these three matrices, you'll get this form. So this is a real, already you have done. Now we are going to do in the complex quadratic form in CM. So here the quadratic form in CN means just entries are going to be here, or this one, this one, these are going to be the complex. Okay, and if you see it here, if you've gone through with the lecture, because now today is Thursday, so I hope all of you have gone through with the, you know uh, content at least till here. So you can see in place of t now means here we can write this one as, we can say, and this is nothing but, let's say this is a vector v. So v transpose a matrix v. This is what it is. A is this one. V is the same this one. So here it is transpose. Now if we are in the complex, so in complex, in place of this transpose, we'll think about Hermitian. So this Hermitian will come now. So this V Hermitian A V. So here professor is writing X. You can think as uh, V, or I can also write just X. X is going to be a vector now here. X H A X transpose. So this form is uh, here in place of real. We are thinking here as a complex entries. Now we'll think here the Hermitian. My voice is clear and all of you able to hear. Good. So now here all of you can see it here. See, Hermitian means Hermitian means the transpose is coming there. Halide transpose and conjugate. So conjugate would be there because we are playing on the complex. So you can see it. So this is what it is. But the thing is, the question is why we are studying. This is a useful, very very useful. Sometimes So here in the case of this, the quadratic forms, we are studying only the this have the broader meaning. Maybe you will see some other course the use of the quadratic. Actually, see here we are only dealing with this function, but when we are going to in the calculus part, I am saying uh, eigenvalues. So we will use this matrix, and using the eigenvalue and eigenvector will uh, tell something about the stationary point, critical points. You know already the what are the critical points in maths one. So eigenvalues, eigenvector will help. Here, whatever so there, all of you didn't study the multivariable. So this is a kind of multivariable function, no, quadratic multivariable function, and using this matrix will tell something the maximum minimum value when the matrix is positive definite. So this relate to the positive definite matrices also. So we'll see more slowly. If not here in this course, you can see somewhere else, means maybe some other courses. Okay, so uh, so professor is introducing here the Hermitian. So this A matrix, so I just so in the case of this one here, when we are thinking about this form, when we are thinking about this form, this matrix A is going to be Hermitian matrix. Okay, this is always going to be a Hermitian matrix. So why it is so? Anyone can comment it here. Why it is so? The reason is this matrix AC. First, we are studying this one. Okay. So in the real case, I am saying we first started studying this kind of function. Okay, quadratic forms, and then how it's generated. Actually, we first started studying this, and then we back to this form. Okay, this form. So if you see how this matrix is formed, this matrix is actually symmetric matrix. If you see, from this form we generated a matrix which is a symmetric matrix. Okay, so we are connecting this form in linear algebra. Okay, this form is a this this is a function. Okay, this is a quadratic function, a quadratic polynomial. That is why it is called quadratic form, but also that the quadratic function. But we change this, not changed, we are thinking this form in linear algebra, so that is called quadratic form. So how we built it, this matrix. Okay, see that how this we not the generator like we started studying this one. So how he built it, this matrix, that is the reason this building means here this form, from this quadratic form we reaches to, we connect with the linear algebra, and this matrix is uh, we got. So if you see, this matrix is always going to be symmetric. Okay, so the reason is here, if you check, always we want to connect this form, if it is in the complex case. So this is always going to be Hermitian matrix. Okay, this is always going to be Hermitian matrix. And even uh, this is the case here. uh, that's all about this her this form. Actually, quadratic form is nothing but just that studying this form only. We mostly see whenever somebody is given, no, somebody the question is be asked. You can check in the activity. You can check the activity problems. So it is given. It would be given some expression. Okay, maybe in the two variable case. Let's say x square plus 2xy plus plus y square. Let's say this is set the quadratic form is this one. Write this in the matrix form. It's here in this fashion. So this is going to be x and y, and what is going to be the matrix? So matrix entries you can think it here. So here is 1, here is 2, and here is 1. So this is going to be 1, 2, 2. Sorry, this is 1. So this is 2 time 1. 2. This is 2 here. So we can think 2 as a 2 time 1. So this is 1 here. Okay. This one, this entry came here. This one, and this one. This C part is here. So if it is this form ax square plus 2bx plus cy square, then we generate, or the form is going to be this one, a b b c and x and y. So, okay, so generally ask that, okay, so what is going to be this form, x, or even v, if you are writing here is x already there. So v transpose a b. So this is our a. So here in this case, this is our a. Okay. So why we are studying this is have some property. Okay, so this Hermitian matrix have some property. So what is a property here? So property is that if we have this a as so main studying is the Hermitian, this matrix a, this matrix a. So this property had, this have orthogonal eigen vectors. Okay, we have this Hermitian matrix, so it have orthogonal eigen vectors. This is the main property here. Okay, so I hope you know already. So many times we are done till now. Week 8 is over. So I have seen many of your. So the quiz 2 actually tells you. We have seen. I have checked some copies also. Many of you are not able to find the eigenvalues, eigenvectors. One simple circulant matrix was there. Even no need to do with finding the eigenvalues, eigenvector. If you use just property of the circular matrix, you can easily get one eigenvalue and one eigenvector. And many of you are not able to find the left null space. And the least square, very less people have solved the least square solution. That is the only problem on the least square given in the matrix form itself. Just need to do a transpose ax is equal to a transpose b, and just solve the system of linear equation which is of 2 cross 2. So one thing is there, yeah, one question is a bit not hard. Numerically, you have to do a more calculative. You have to find the eigenvalues, eigenvectors for 3 cross 3. That is the only, not, I will say, not a tough problem, a bit lengthy. But very less people able to get that. but we are trying to, if somebody's wrote something related to that, we'll try to give some partial mark. Okay, but the thing is, at least you should to write there something. Okay, so yeah, we are talking about the eigenvalues, eigenvector of the Hermitian matrix. So eigenvectors are going to be here. If your matrix is Hermitian, this matrix A is Hermitian. Okay, means if you do what is a Hermitian matrix, so if you don't know, it is just a definition. If you do conjugate transpose, which is a sign of AH, you are getting this, then it is a Hermitian matrix, and it have real eigenvalue. So Hermitian matrix property have that it have real eigenvalue, even it is in the complex, and these are complex, but eigenvalues are going to be real, and the eigenvectors are going to be orthogonal. This is a property of Hermitian matrix. So here it is, a professor is telling if your matrix is no ortho. So once we got the eigenvector, we can make a matrix. So if we got the eigenvectors, so professor is saying if our matrix A is Hermitian, then we'll get a set of vectors. We are able to get a set of vector, which is nothing but talking about the eigenvector. Okay, and indirectly he is saying that we are talking about the set of eigenvectors. Once we got that, we'll form a matrix using the eigenvectors. Okay, let's say we have this eigenvector u1, u2, un. So we'll form a matrix. Okay, this matrix is orthogonal. So I think professor is divided by the norm or not. So he's talking, so if it is orthonormal, so the word uses orthonormal. So if it is not, so here eigenvectors we got orthonormal, we can divide by norm. So it become a orthonormal. Uh, so if we get the eigenvector, let's say u1, here it is, this one, you can divide by norm. If we divide by norm, then it will become orthonormal. So let's keep it here as let's form the matrix using this orthonormal vectors. So this matrix become this matrix which we found S. This matrix S is a called orthogonal matrix. What is the property of orthogonal matrix? The property is that if you find the inverse of this matrix, there's no, which is nothing but the Hermitian of that. That's all. Okay, this is a property of normal matrices. Sorry, orthogonal matrices. So here is professor is talking about what some type of matrices, like if you form this is, so this is here. So if you, the inverse is going to be nothing but the Hermitian of that. I don't know all of you are able to catch or not. Okay, difficult. Yes. That is why actually who are able to correctly reaches to the characteristic then we'll get some more marks. Able to find the eigenvalues, eigenvector, get the more marks. So this problem is a bit calculative, but if you are able to write more steps, you'll get more marks on that particular problem, and rest all questions are fine. So at least one question is there which is not tough, but yeah, a bit calculative. Okay. Okay, so main purpose of this particular lecture is uh, studying this form. Okay, and then this matrix is going to be a Hermitian matrix. Okay, and this Hermitian matrix is nothing but, if you do Hermitian, you will get the same. Okay, this is the meaning of Hermitian. So this Hermitian matrix have some property. The property is it have real eigenvectors and real eigenvalue and eigenvectors are orthogonal. Okay, this is a main theme of this lecture. And the second is, once we know that there is another matrix which is a unitary matrix, which I was saying, no, orthogonal matrix. Unitary matrix is such matrix, or we call unitary matrix to those matrix which is have this property. If you have, let's say, U, okay, and if you do Hermitian and U, okay, with the same matrix, means if you are multiplying same matrix with the Hermitian, we'll get identity. Okay, and in the different word, it is nothing but inverse of this matrix is nothing but the Hermitian. You can just connect these two are same. And this unitary matrix have this property that if you check the columns, no, columns are going to be orthonormal. Columns are orthonormal. So this is a property. So these two properties are actually professor is trying to tell you the Hermitian and unitary matrix. Okay. So if you have a Hermitian matrix, okay, so the word, what is the final thing is that, see, here is the orthogonal, no, orthogonal. So what is the thing is that if you have Hermitian matrix, you will find the real eigenvalues and eigenvector which are orthogonal. Okay, so orthogonal, if you divide with the norm, it become orthonormal. Okay, then what we can write, this matrix A, we can write U. Okay, U, professor is writing yes even, so we can, let's say, U or yes, whatever you can use. Why I am writing U? Because this yes, diagonalization P D P inverse. So here this our P is how we used to form using the eigenvector. So this P is going to be our unitary matrix. No, we are filling with the orthonormal vector. So here these are the orthonormal eigenvector. If you fill this will be a orthonormal. Sorry, this will be this matrix which this P is actually nothing but a kind of unitary matrix. It will be because it contains these properties. Okay, that is the professor saying. So Hermitian matrix are actually unitarily diagonalizable. Simply word, Hermitian matrix are unitarily diagonalizable. Unitarily diagonalizable means this matrix P is a unitary matrix. Why? The reason is because Hermitian matrix have orthogonal eigenvectors. That's all, as we have seen in the symmetric case. So go through with the all lecture. You will now. I hope all of you able to understand properly. Is this clear? Not clear? You please comment so that if not clear, I will repeat it again. No? Okay. In this quiz too, at least I am happy that all of you are right the steps. So many of you have written the steps for everything. Many, if they are who is able to solve, wrote all steps. So it is a good thing that at least you are writing the steps. If you are writing the steps, you will get the marks. Just wait. In the next lecture, uh, oscillation modes in the system. This is just a theory part. This is totally theory. Uh, Professor is telling about if you have this kind of system, we can think it as some this kind of a function, and we'll try to solve. So here, if you see it here, the question is based on we want to solve only the uh, or this is a one of use of how we can think a system, this kind of uh, electrical circuits or something we have, and we can convert in in the linear equation. Means telling about the linear, sorry, linear algebra and this electronic system. So this system have this, we can convert this kind of equation, which is kind of partial, or even it is in one variable case, then this is a differential equation. So it have some even this kind of equation, which is derivatives contain the derivatives, a differential equation it is called. And here omega have some we can think as frequency. So you will more you these all you are able to connect more once you have already, or even have already this kind of courses. And one course, a head course, which is totally based on this maths too. Something, what is the course name? System, what is that course? Which contain more linear algebra part. System one? No, system one. Yes. Some courses there. So here, what is the purpose? Is that is we can connect. We have this kind of uh, electronic system. This, and we'll relate with some equations. This is some law is there, no? And once we have this, we can, which is a kind of differential equation. You can see it here. This one, which law already given the differential equation, and now we can convert this system, these equations in the matrix format. This one, we have two equations. We can think, or we can convert. See how it is. Differential equation to symmetric matrix equation. So we have some uh, circuit, okay, and using that some differential equation we got, we can, which we can think as a linear. You can think in the linear algebra form. We can form a matrix like see, this is a simple use of this one, this quadratic form, as there you used to see each term is some quadratic when it's degree 2, and we converted in the matrix form. The same way here we have a differential equation, and we relate to a we relate to a matrix. That is what it's happening. That's why the quadratic form you studied, and now you are able to relate with this differential equation matrices. Now see, in the inner part there I was saying, no, this is going to be Hermitian matrix, or where is that? This one. I was telling about this in this form. This matrix is symmetric matrix, and if you are dealing with the complex, then this matrix become Hermitian matrix. So this is what it is. This is a, we change this system in this differential equation, this matrix format, which is a symmetric matrix. And now once we are related to the linear algebra, means matrix format, then you can see always, so at many places we'll see use of eigenvalue, eigenvector, eigenvalue, eigenvector, and this matrix will be simplified using the eigenvalues, eigenvector. We will diagonalize it. If you see, the professor is finding the eigenvalues and eigenvector, and now he diagonalize it. The eigenvalues are 1 and 1 plus 2a. Here is alpha, it is, so alpha. 1 plus 2 alpha and 1, and eigenvectors are this one. And this is a symmetric matrix. You can see if you do dot product, this 1 and 1 become 1, and 1 and minus 1 become minus 1, and 1 minus 1 is 0. So these two vectors are actually orthogonal. Eigenvectors are orthogonal. You can see it here. Eigenvectors are orthogonal to each other. Now divide by the norm. Norm is going to be, many times you have done. So divide with the norm, which is root 2. So it will become orthonormal. We form the matrix. Now this is the uh, matrix using which formed by the eigenvector after dividing by the norm. Yeah. So this is a orthogonal or unitary, you can call it. This is your unitary matrix. This is your diagonal matrix, PDP inverse. So this simple matrix change in the this form. Once it is changed, now system of this that differential equation is bit simplified. Now already that whatever the this one sent to this side, this one is some manipulated. Now it's better to see the lecture. So this lecture is a totally theory part telling about once you have some electronic circuit system, you can change in the, or you will get a system, sorry, differential equation. You can change that differential equation in the matrix form, and once you form a matrix form, then find the eigenvalues, eigenvector, make that system differential equation in the simpler form, which is here. You can see once we change, you can multiply and see this is the simplified form. What this is what it is. So this is a totally theory part, and where there is no numeric or there is no linear algebra is happening. Whatever the linear algebra is happening already done week 1 to 8. Okay. So my request is please go through with the lecture. This is very simple lecture. You just need to listen. If you're not, no, here is nothing is happening. If you see the question is also not asked in the based on this. You just need to know, or this is professor is telling about how we'll connect the quadratic form with the this uh, electronic system. That's all. Or why we, whatever we studied here quadratic form, that is what the relating thing. That this matrix, the inner part, this one is our symmetric or Hermitian. It has some property that eigenvalues are real and eigenvectors are orthogonal, which we change as orthonormal. We can diagonalize it using the orthonormals, means PDP inverse, and make them a simplified form. That's all. So that this lecture is totally application whatever we studied. The new thing is that we are going to see this correlation and covariance matrix. So correlation and covariance matrix is what? Simply we have some data. The professor started also with the data. This is a bit statistics. The stat part is there. Simply, what is that? We have, so let me show you. I mean, I write also. So we have some data. So data means, in uh, coordinate. Okay, coordinate plane we have seen, where the point we denote as 1, 2, 3, 4. Like this we used to denote the point. Okay. So we can write in the more formal way. How we'll write? The x is 1, 2 is y, 3, 4. Okay. This 3 is x side, y is So let's say 5, 6. So studying this type of called data. So this is we can call it as a data, or we can call this one as a data. So this is a data, or we are naming it as a data. So this is a data. Okay, this is the data we have, the points we have, these points we have. Now see, these are the point. If you think this is a kind of vector also, 1 2 3 4. Okay, this point we can think as a vector also, 5 6. So this, so many things we can call it as a point data vector. So all are at the same point it's happening. If you are writing this form, you can call it a data. This form is a point vector. This form is a point. So it is a convincing way. However, you can interchange to like you can change to the you can call it as a data points, whatever you want to say. You can tell. So now I'm just naming it as a data. We have some data. We have formally. This form is we are going to study, or we can write this data as this form also. So we have some data, 1 2 3 4 5 6, as the professor is saying. Okay, we have some data. Now we will see some relation using this data. So if you plot these points, so we have this or points or vector. If you plot this vector or point, so if you point this plot this points, we have 1 2 maybe here, 3 4 maybe here, 5 6 maybe here. Similarly other point. Okay, we have some other point also. So this tells you the relation. What kind of relation? This tells you the relation. If suppose your data is more like this side, only this. If your data is like this, what it tells you? It tells you if your x is increasing, y is also increasing. See that x part is increasing, y part. This is your x-axis. This is y-axis. So x is increasing, y is increasing. So means what you can say, x and y are related. Some relation is there, so that when x is increasing, y is increasing. So there is a relation, or there is a correlation between them. That is what it is. There is a relation between x and y. We can say they correlated to each other. Okay, this is what it is happening. So it is just an introduction, but we are going to deal with numbers only. So if you have some data, we have, let's say this is the data we have. Using that, see how it is. We already done with the so now what we can do, this is the data we have as here. Now collect all x coordinates here, this side, and call it as x. Collect all y coordinate, call it, okay, call it y. Okay, this y side is one part, x side is one part, x is and y is. Now this relation, inner product, we have already studied. Inner product between x and y and divided by the norm. Okay, this formula, whatever we'll get here, this is a real number, this is a real number, we'll get a real number. This is called correlation between x and y. This formula is called correlation between x and y. So in theoretically, what I am meant to say, we say suppose we have a data, this one, I am forming x as 1, this one 3, this one 5. This I collected here, y is collected here 2, y is equal to This 2 is here 2, this 4 is 4, and this 6 is here. Okay, we have this 2 now. You can think this is a kind of vector now because it is listed, or even we can write like this. If you want, we can write like this 2 4 6, like this. All of you know the inner product thing. What is the inner product between these two? So now there is a question: what is the inner product between these two? Anyone? Anyone can tell what is the inner product between these two?
44.
24. Somebody is
44.
saying
44.
okay, let's see that. Yeah, 44. So nothing but because all of you done the inner product now, so means direct multiplication, coordinate wise multiplication, and add them. Means here 1 into 2, or if you write in the formula wise, so this is nothing but y transpose x. Okay, that is what it is. Means matrix multiplication. So if you do, it will be here 1 into 2 plus 3 into 4 plus 5 into 6. So 2 plus 12 plus 30, which is 44. So this is what is happening, and divide by norm of x, norm of y. So what is the norm? So I am very disappointed with that many of you are not able to find the norm, because there is one MSQ and a T question in an quiz 2 where we have to find the norm of a plus b minus a norm of a minus b. So many people not able to find the, not many, but at least 20% student, what is the norm here. So in this case here norm is, at least you should to know what is the formula. In this case norm is 1 square 3 square root of this, and norm of this one is going to be root of 2 square 4 square 6 square. So simply if you have vector a b c, okay, norm of this vector is nothing but, let's say this vector is v, so norm of this vector is nothing but a square plus b square plus c square. So this is what it is happening. So divided by the norm. We divide by the norm. So if you divide here the norm is going to be 9, and then 25, 34, and then 1 35. So this is, so we got already. So 44 upon root of 35, and another root is this one is, this is 36, 4 plus 16 plus 36. So this is 52, and then 456. Yes, root of 56. So this is, so whatever we got this real number, this is called normalized correlation between x and y. Okay, this is what it is. So, or it is in the real world, this is what is happening. Means we are, what is happening here, this number tells you if it is more intended to one side, then it is related more. Okay, highly correlated, less correlated, we'll see in the ahead, we'll see. So this is what it is happening. It means related or correlated means if x is increasing, y is also increasing or maybe decreasing. It's depend on how it is the data. Okay, so this is just a formula you can remember. So these all you can remember easily. This is some constraint is given, you know how it is happening. Now this correlation, whatever we studied here, and we can study in the different manner also, in the co-matrix form also. So that is called correlation matrix. And how it is see formed? This is formed like this. How it is? Simply it divide by how many data we have, and data we have divided by the n. Okay, and this is what? X1, Y1, vertical, here it is, and then transpose of it horizontally. Okay, so simply if I will write here what is happening, suppose we have a data which is x1, y1, x2, y2, xn, yn. Okay, we have a data this one. Let's say this is v1, v2, this is vn. Okay, so correlation matrix, which is I'm denoting at rxy, which is nothing but the matrix 1 by n. If we form like this v, so here, so think is if it is a problem, think as a x1, y1, x2, y2, xn, yn. So v1, v1 transpose plus v2, v2 transpose plus vn, v1 transpose. This is what? Or simply x1, y1, and horizontally x1, y1, x2, y2, x2, y2, xn, yn, xn, yn. So this will be a 2 cross 2 matrix. If you multiply this, will get 2 cross 2 matrix each time. So finally, if you add them all, you will get a 1 by n or 2 by n. You can remember that formula from the lecture if you want. Otherwise, no need to remember it. This is what it is. This matrix is called correlation matrix. Mean variance is many times, all of you are from maths background till 12. So you know already what is the mean of data. Just add them and divide by the number of data. So I'm not going to tell you variance is nothing but subtract by the mean, each data subtract by mean, and divide by the number of data. You square them and divide by the number of. So you know already this mean and variance many times because you are from 12th. But only the new thing is that the correlation matrix and covariance matrix. So mean and variance is just a formula. You can see it there from there, are already done also. These are all just formula. This is already in 12th standard. So mean is already sum them all data divided the norm, and here correlation between x and y denoted by this row xy, which is inner product we have already did just now. So correlation between x and y. So updated one is subtract by the mean and divide by the this one. Here it is. If you call it as this is the updated data. So we have a data, centralize them. Centralize them means subtract by mean. We have a data. Okay, this one subtract by mean. X side x mean, y side y mean, and now it is called centralized data. And find the correlation between the centralized data. Means use that formula, inner product between them, divide by now, and this sigma, this one. Whatever we just now seen means this is an updated formula. That's a small updated formula, but telling about the same. Only divide subtracted by the mean. This is the only formula, but updated one. So these are just a formula. So this is a correlation coefficient, it is called. I hope all of you are able to get it. This is just a formula, numeric formula. It is. There is no theory. The new thing is a covariance matrix. So covariance matrix is either you can remember by this formula or simply you have a data. Okay, suppose you have a data same x1 y1 x1 y1. Okay, find the mean of x side, means here 1 by n x1 to xn. This is a mean called y side. For y side is 1 by n, add them and divide by the n. This will be the y mean. Now subtract centralized data, use the centralized data. Okay, so x1 minus x mean. Okay, y1 minus y mean. This is now centralized data. Similarly, xn minus xn mean, yn minus y mean. Okay, this is called centralized data. Okay, once we did this, now simply use formula. This one, what is happening? See that how the centralized data is square there, multiply the separated one. Okay, and here it is multiplied by the separated again. This is a symmetric matrix. You can see this is a symmetric matrix. See that it is symmetric matrix, and this is y side. What I mean to say, the covariance matrix is going to be, or there is a different method also. I think professor wrote the formula somewhere or not. Yeah, here it is, covariance matrix. This is the updated one. Let's use this one. No need to remember that how it is. So it is nothing but the this is what is how we wrote the correlation matrix, no? Plus side and then transpose on the same. This is for n dimensional. Okay, so here it is. Professor is wrote or not? Okay, what happened? Am I audible? We can use this formula. So whatever the correlation matrix we wrote, no, if you use the centralized data, then it will be a covariance matrix. That's all. Means here we use, no, this one. See that this is, so we did on this without doing any separated mean. See that this is the same, no? Once we subtract them, okay, this is the updated data, means centralized data we got. Now 1 by n, let's say this is or simply we can write like this, x1 minus x mean, and if it is this one, x1 minus x mean, y1 minus y mean, and x1 minus x mean, y1 minus y mean. And so if you see, this is the same thing, same formula is there, only here is the a subtracted one, means centralized. We are writing the same formula on the centralized data. This is called covariance matrix. Okay. So correlation matrix is on the original and covariance matrix is on the centralized data. Am I audible? Okay. So this is what it is. That's all the correlation and covariance and correlation matrix. Why are studying this all, you will see later. You will see the use of it in a later case. Okay. So these two lectures actually, and the rest two will try to cover on Saturday. Otherwise, nothing would be there. So we'll see the graph and adjacency there, and positive definite matrices. Positive definite matrices are nothing but just a matrix you have, and it have the eigenvalues. Again, you will see the use of eigenvalue, eigenvector. Positive definite matrix is nothing but it have the positive eigenvalues. And adjacency matrix and graph and adjacency matrix, there you will relate the graph, the matrix, and once we have matrix, we'll find the eigenvalues, eigenvector. If the eigenvalues, eigenvector have some property, means you have eigenvalues as a 2 minus 2, 4 minus 4, 6 minus 6, kind of this one, then that is called bipartite graph. So we'll see more on, very, so linear algebra is very, very applicable in all, in even the maths itself. It is used to, we usually use in graph theory, some other course, stats, data science, the law of maths. Sorry, linear algebra only. So is this clear? Not? If you have doubt, please let me know. So one question is leaving. I am leaving for you. So we have already this one. This is a data. Let's say 1, 2, 3, 4, 5, 6. Okay. So I am just, all of you try it. Find the covariance matrix. All of you try it and let me know what is the covariance here. Covariance matrix 1, 2, 3, 4, and 5, 6. All of you try it and let me know what is a covariance matrix. Okay, you can see the question. All of you please try this and let me know what is a covariance matrix. Have anyone tried this? What is the covariance matrix here? No? Okay.
All elements are 8 by 3.
Sorry.
All elements are 8 by 3.
8 by 3 covariance matrix, I'm saying. Okay, all
Yes.
elements are okay. Okay, good. So all of you try it. You can expect a question from this section. Okay, at least covariance and correlation matrix in interim exam. Okay, so try to do it. Try to practice it. Okay, so this is an important section to do. Okay, good. All entries are this is easy, not tough. If you do quickly, so here if you find the mean, so mean is going to be for x portion it is going to be 1 plus 3 plus 5 divided by n, which is 3. So this is 893. What is a y mean? Y mean is going to be 2 plus 4 plus 6 divided by 3, which is 4. Now that centralized data, okay, centralized data is going to be 1 minus 3, 2 minus 4, 3 minus 3, 4 minus 4, 5 minus 3, 6 minus 4. So this would be minus 2, 0, 0, 2 and minus 2. Now the covariance matrix is going to be 1 by 3, which is this one, minus 2, minus 2, minus 2, minus 2, minus 2, minus 2, plus 0, 0, 0, 0, 2 minus 2, 2 minus 2. So here 1 by 3, and this is 4, 4, 4, 4, plus 0, 0, 0, 0, plus 4, minus 4, minus 4, 4. So is this each entries or diagonal entries? So this is 8, 1 by 3, and this is 4 minus 4 is 0, no? 0, 0, 8. Is it? Am I doing wrong? Is this correct?
So the last part should be 2 now. 6 minus 4. So the last vector is 2, 2.
Oh, here it is. So yeah, 6 minus 2 I just wrote. So this is 4, 4, 4, 4. So it will be 8. 8. So 8 by 3, 8 by 3. So this is a covariance matrix. So see, either I did so by this formula, or you can remember with the sigma xy, sorry, sigma x, sigma y, sigma xy, something is there, sigma x is, so some formula is there. Either directly you can use that one, or with the simpler way which I use this. Okay. So that's all for today's session. I hope able to understand. Anyone have any doubt? No? Very silent. So again, I will suggest you, without practice you cannot do for interim. If you practice it, then even the big question, bit calculative question, you can easily do. Okay. So anyhow, so if you want to complete this as subjective problems without writing, you cannot do. So you have to practice at least for writing, so that you can write in the exam in very fast manner. And if you are writing mathematics, so be organized and try to write the all steps, so that will get marks. So without practice you cannot do. That's why the lot more assignments you have, but all of you, like many of you used to just copy and write, or many of you used to just write the answer in one step. If you hide, then you will face in the exam. That's all. That is what is happening. If you'll, so all of you requested for subjective maths 2 as a subjective course. That is how it's happening. But still all of you are hiding, or you are trying to skip the practice one. Then you will face, as all of you are facing also. You have to do practice. Without that you cannot. Okay. At least try to write yourself. So try to write assignment by yourself, so that you are able to write in exam. Otherwise no, then you will face. If you are not writing assignment by yourself, then you will face in the exam only. It doesn't matter if you are not doing here, then you will face. If you are doing yourself, then you will not face in the exam. Questions are, you can see your questions are not tough. Like all of you are not able to do at least that least square solution problem. I don't know what is the issue. You just have to do A transpose A and the simple theory. Many of you are not able to find the correct answer. This shows that lack of practice. That's all. Many of you are not able to find the left null space. Is there, if it is, now the qualifier exam in DS now a bit simplified. If you see in the old new qualifier, the first time qualifier paper or in DS, if you see that, then this time is what is that very simple. In starting, it was very tough because whatever taught there, it is some twisted. The questions have some twisted. Here, it is a direct question. You have a matrix. You have to find the eigenvalue. You have a uh, given the matrix or system of linear equation. You have to find the least square. Suppose we mixed with some context, then what will happen with you? The direct problem here it is given. If you mix with the system of circuits problem using the context circuit context, then how you will do? I don't know. Without practice, you cannot do. If you not practice yourself, then you'll face an exam. That's all. Okay, thanks everyone. Thanks for joining. We'll see you on the next session.